Okay, microphone seems to work. Excellent. I've just learned that I've got 25 minutes, not 30, so we'll do that. I welcome questions along the way. If I notice them, then that's great for some interactive discussion. I'm splitting my time between the European Excel in Germany and university in England, and there are people contributing to this work from both places. This is my shorter title because the first one was a bit long. So an aspect of this is that I'll be talking about reproducible computational science with Jupyter. I'll start with an outline. I want to give some motivation why we care about the topic. I will use the particular example of simulations of magnetic nanostructures, and that's why I need to talk about something called the object-oriented micromagnetic framework, short OOMMF, which is an existing simulation tool which we want to use, but which is a little bit old-fashioned in its ways. I like it, but it is an unconventional interface from today's perspective. I'll explain what a typical computational workflow for the researchers in this field would look like, and then demonstrate or show how we connect this package through a Python interface to this audience here in a way, and then demo that and close with some observations at the end. Computational science and data science are becoming increasingly more important and more widely used. And it's a research interest of mine to look for methods to improve that, to make things effective, more effective, better. Because the question is, what is better? And so you can say, okay, faster to use, more accessible to a wider audience of scientists who may not be trained with computational methods and programming. Or, of course, there's a growing movement of people who say, we really must make sure that computational science is also reproducible, which isn't always the case at the moment. I'll try to give a live demo, and if anybody wants to join and reproduce along on their own device, they're welcome to do so. If you go to this link, this should start up a process that takes a few minutes, and we can use that in about 10 minutes then. What's the story with reproducibility? Often results are not reproducible, which means we carry out a study and we publish it, and 2 years later we ask ourselves, how did we actually get to that second figure in this work? And nobody can remember, and the right PhD student has left, and the scripts are gone, and the Fortran program nobody can compile, and we don't know which things belong together. And so reasons for that are just the complexity of the workflow. But if you talk to people, they also mention other reasons. Some of them are questionable, like basically saying, you know, if I tell everybody what I do, then they can do it too. So that doesn't help me. That's a questionable approach if we use the taxpayers' money to carry out this research. There are other comments where people say, well, I actually don't know how to do that very well, or it's too much work to document all these things to be able to reproduce what we've done before. And so what I want to show along the way is the binder project, which was introduced yesterday by Tim Head in a very nice talk, and that's what we need this link for, and this will help us some way to address that combined with notebooks. Moving on to the introduction of the scientific field, which is called Micromagnetics. It's the study of small magnetic things, and computational modeling using computer simulations to understand them is an important part of that. Why is that interesting? There are basically two views of this. If you talk to a physicist, they would say, oh, it's a fantastic system. There's so many parameters, so many competing interactions. There's rich physics. We can play with this, and there's always something new to discover. And when you talk to an engineer or material scientist, or if that physicist needs to apply for some funding, they would say, aha, there are applications. We can build magnetic data storage, and we can heal patients, and we can invent the new type of electronics that is called spintronics, and is not based on the charge or the spin. And indeed, this is a magnetic medium in a hard disk, and this is the simulation of a process of writing a bit. And so the blue thing is maybe a 1, and the red is a 0. And you can see that it's a little bit messy when you stop writing the process. And so this is all simulated, and people do that to improve magnetic media. When we run such a simulation, we may get outputs like this. There's essentially one magnetization vector for every point in space. This is a 2D view, but you could also simulate 3D systems. This is a visualization of magnetization in a sphere. Mathematically, we describe this with a continuous function that is defined everywhere in space, and so for every point in space, we get a 3D vector, which is the magnetization, and it's also typically time-dependent. And then there's some more equations, which we haven't got time for, and we can put together a Hamiltonian, which is the physics way of talking about the interactions that happen. And I want to give you some feel for the complexity that can arise here by showing simulation results from a 1D system. So we align a set of moments along this direction, and we start them from random positions. Let's do that again. And they behave in the 4 examples differently because they're exposed to different interactions. You could imagine this comes from different materials. So up here, they want to align with the up direction because this is an external field, as the planet Earth has one. Here, the moments want to point in the same direction. They don't care which one that is. These want to show a 90-degree angle from one to the next. And here we have this interaction and that combined, and you see this spiral or helix is a compromise between this 90-degree angle and the 0-degree angle between nearest neighbors. And that's just a 1D representation of these systems. If you go to 2D samples, you can get interesting emerging phenomena. So here again, we start from random positions and we get uniform alignment here and there. And in the center, something shows up which is called a skyrmion and looks like that. And these skyrmions can move around and behave like particles, and you can have solids and liquids and gases of these skyrmions. And it's a whole research area that has emerged in the past 5 years. So people are interested in this field. There's some equations which are partial differential equations, and again, we don't need to worry about those because a nice team of people has invented this software, started about 20 years ago, which is OOMMF that we mentioned before. It's quite widely used. It's developed in the US by the National Institute for Standards and Technology. It's publicly funded. The motivation was to support industry so that they could check that their own models work like this one, assuming that this gives some reassurance that they work correctly. It's been used over 2,200 times in scientific works. It's written in C++ and TCL, and it has a web page. It's driven through a configuration file. There's also a GUI, but it's not as powerful and not so reproducible. And this configuration file is essentially a TCL script in which one has to follow certain conventions for defining things that this OOMMF simulation software knows about. And when it starts, it reads this file and then carries out the calculation in C++. To put this better in context, I want to describe a typical scenario. And we take one from what is called a standard problem. This is a set of problems that groups of scientists have defined as problems to benchmark their simulation software. And here we have a magnetic cube of some size, and the magnetization in there can exist in 2 different configurations. One is the so-called flower state, which is shaped like a flower, and the other one is a vortex state, and they're both stable. And picture looks a bit dated, and in fact, this is from 1998. The web page is still up, and it just looks like that. This is a screenshot. There's some interesting history here. And if you want to solve this problem, you basically need to set up a simulation with this vortex state and this flower state, and you let the system relax in each of those configurations so that it's stable and finds the local energy minimum. And then you vary the edge length of the system. So this is a 2D cross-section of the 3D cube. And as you do that, the total energy of the system will change. And if we vary the edge length and we plot the energy, we see that the energy of this vortex state goes down faster than the one of the flower state. And there's some point where they cross, and this is the point we want to find. And that defines this. If your simulation gives the right number here, then there's a good chance you got it right in writing that code. And how would you do that in this OOMMF package? You take your favorite text editor or some other application, and you edit a configuration file where the edge length enters and the initial state. This is the name of a function that is used later on in this file. So we're trying to compute this one data point now, by the way. For edge length of 8 in particular units, we want to find the energy. Then I execute the simulation. I need to use the TCL interpreter, and this is a path to the actual TCL file and some arguments that are needed. This is the name of my configuration file. And when this simulation finishes, I get an output file, which is called like this, and I need to look into that. This file consists of columns, and we can't see that because the lines are wrapped around. There are many columns. And one of them is called oxy conjugate gradient evolve total energy. That's the one we're interested in, measured in joules, and this is the number. That's the number I need to take, and I put this into a table, and this is the first energy for this data point. And now I need to repeat this for all the other entries here. And then I can create this plot, and I can look where these two lines cross, and that gives me a number. So it's a typical workflow of having some configuration file or script, executing it, reading the results, and then doing some post-processing. And the idea here is that we want to improve on that, because, as I described it, it's a manual process, and maybe this audience would say, you write a script to do it. But that's actually not so trivial if you are not trained in programming. And the target audience here are typically not computer scientists. So what we do is we provide a Python interface to this object-oriented micromagnetic framework, and then we integrate this with the Jupyter Notebook. And I should ask why Python? Again, this is the wrong audience to ask the question, but there are actually some indications that Python is a language that goes well with non-computer scientist people, like engineers and physicists. I've done some field studies a long time ago with first-year undergraduates who didn't have any bias. And at least given the choice between MATLAB, C, and Python, it was clear what worked best for them. The Python interface to OOMMF, there are various ways. It's basically C++ code, and we could connect this at a low level using SWIG or directly or some other tricks. But in the end, we ended up communicating with OOMMF via the configuration files, which is embarrassingly simple, but also quite robust, because we only rely on the defined interface of these files. Within Python, we have decided to have two different classes, essentially. One that describes the problem, the physics of the problem, but doesn't know how to solve it. And then there is a class that inherits from the first one, which also knows how to solve this problem numerically, and this would then communicate with the OOMMF software to obtain that numerical simulation. Okay, so let's look at a demo. This, the software we've created, we've called JUMF for Jupyter OOMMF. It's difficult. It can be installed via Conda or directly, but then one needs the OOMMF executable. We also have a Jupyter Hub instance under this address, and for today, this is the moment where we want to use this link, which I should have clicked before, but I didn't, which will now start up the binder thing. If this is fast, I will use it. If it isn't, I'll use a local copy of that. Maybe I'll go with the local copy, because we only have 25 minutes. So here's an example where we set up a simulation system, and is the font large enough for the last row? Yeah, thank you. And for example, we create this Hamiltonian that contains some interactions, and we can ask what the Hamiltonian looks like, and exploiting the rich media in Jupyter Notebook, it displays this as an equation which pleases the scientists because they know what this is, and it's a kind of structured object, so we can extract particular parameters, or if we want to have some code that can recreate that object, we can also do that. I didn't talk about the dynamics, so let's skip over that. If I want to go to a numerical solution, I need to discretize space, so I need to create a mesh. The mesh we also visualize in the notebook. Our discretization cell is the red one here, and the blue thing is the total volume that is being simulated. And when we have that, we can define a magnetization field in a discretized fashion, and we can plot that, and the moments are all pointing up because we said the initial value should be 0, 1, 0. The y direction being up. And now we're asking for the numerical solution, we're asking how would this magnetization behave if it could do what it wants in this sample, obeying the laws of physics. And this is where we actually call the OOMMF simulation software, which took only 2 seconds here. And this has now updated the state of this magnetization. And if we plot the outcome, we can see it has changed, and the direction has changed, and it also shows some of this flowering. So that's the basic idea of the interface. Moving to a more complicated example, this standard problem 3 that I mentioned before, because we are now in a Python environment, we can make our life a little bit easier. We need to start from the top, of course. We set up functions that create magnetization patterns which will fall into this vortex and flower state as we need. We set up a function that, given the edge length of the cube and an initial configuration, will set up this kind of simulation as we did before. It will minimize the energy and return this minimized system to us, and we can then ask that system for its energy. And so let's in fact run this first. So this is the first energy minimization, giving us the vortex state. And if we start from the flower state, we get the flower state, and then for both of those, we can ask what is the total energy, and there's the value that we extracted from the text file before. And of course, we can now create a for loop, which is here, where we iterate over different sizes of that cube and call the simulation repeatedly, and it will execute the simulations in a loop, create a plot at the end, which shows the two lines that can cross. And we can go even further because we have access to other tools in the Python ecosystem. We can use a root finding algorithm to find this crossing point automatically. So there's the plot. The points are the ones we have just calculated, and I can start a process to give us a more accurate estimate of this point here by using some kind of root finding. Here we used the bisection one, which is quite simple. And then I have a study in a notebook that goes from the very beginning, from the definition of the problem, including the plot and the equations, to the code that we use to implement this, to the actual calculations and results, to this first approximate plot, to a refined search for this crossing point. And when it finishes, it will print us where the value is, and potentially we could publish that, and we can use this notebook to use this in a reproducible fashion. Okay. I will skip the third example, which would just show some time-dependent study, and in that case, we can export the data as a pandas data frame, which is convenient to exploit all the methods that pandas provides. The package is open source. It's structured in a way to consist of multiple sub-packages. It's all on GitHub. So let me spend some time on the discussion of what we've done and the lessons learned. So what have we got? What have we done and achieved? We now have this ability to drive these micromagnetic simulations from Python. And we've gone slightly beyond that and integrated in Jupyter by having these rich media representations of equations and plots and meshes. And I didn't show you that we can also use widgets to explore these configurations interactively. The whole thing is designed in a way that one could also use other micromagnetic simulation tools as calculators. Right, so the description of the physical model wouldn't change, but when we come to the calculation, one could use a different calculator, and that would be quite nice to compare them, to be able to flexibly switch between them to, this one is for GPUs, for example, to use a GPU when we have one, and so on. But we get a bit more for free with that. We have the scriptability of computational studies within Python, which we didn't have in this configuration file-based approach that I showed with the TCL file. We can use all the libraries that exist. We make the reproducibility easier because we have the whole study in one document. We can share these documents and make them executable on the internet through MyBinder, which is the thing I wanted to demo before. And for those who haven't seen it, here's my cloud instance of this particular problem, where if you had a screen and wanted to do so, you could follow through with the same stuff that I did, which I ran locally on my machine here. Okay. It does indeed work. Just want to convince myself. Okay. We can also have remote execution on Jupyter Hub. This is something the European Open Science Cloud is very interested in, to be able to remotely control simulations and data science and data analysis. We can put documentation and tutorials into the notebooks, and then Sphinx will create the documentation from that. We can also make the documentation executable through MyBinder. So users who want to learn about the package can go there and find the documentation with examples, and they can just execute and modify those examples, which is great for a learning experience. We can also run continuous integration on our documentation notebook. So here the idea is that we use a package called nbval, which links to PyTest. And PyTest will essentially go through our notebook and compute what the first code cell does, look at the output and compare the output with what is saved in the notebook file on disk. And if they're the same, it says it's a pass. And that's quite useful because documentation is often forgotten in these projects. And if you have some, you write them in the beginning and then you don't update it later and you don't read it, and so it's out of date. And this will warn us, which is quite nice. Very briefly, wanted to comment on the computer science perspective on this interface that I described. What we've done, you could describe as a domain-specific language for micromagnetics, because this is what this library is. And this domain-specific language is embedded in the general-purpose programming language, Python, which gives us great power because we can combine all the library functions in all the ways we want, but also great complexity because it's hard to anticipate what users will do. So there's also a risk that things can go wrong. Okay, we've given a number of workshops and had activities to disseminate this and get people on board. And one problem seems to be for those who haven't got programming experience that the notebook and Python together is a little bit much to take in, even if we give them recipes that they just need to follow. But for those with a bit of training, this was well received, and having the cloud instances, like the MyBinder example in the Jupyter Hub, was really useful in those workshops because people just need a browser and don't need to install anything on their laptops. Okay. We got financial support from a number of sources, which was important to employ people to work on this. And I want to summarize by mentioning that I did present the work, but most of the work has been done by others, in particular by Marian Beck. We have a publication. There is a repository to which I will put the slides that I just showed, and this also has a link to the MyBinder instance. We're also recruiting at European Exfair, which is a large laser, and if you're interested in that, please do get in touch. Thank you.
So thank you very much for the talk. You did it in less than 25 minutes. Are there some questions? Okay. So if there are no questions, please thank him again.